To tonight's presentation. Unfortunately, not only are we all very gifted students, but one of us is a very gifted athlete, so he's currently representing us at the track championships in West Virginia. But fear not, he will join us via his lovely recorded voice on our presentation. I'm glad to see so many of you have come out. Not really a surprise because our competition is battery thermal management, and I think an autonomous robot is a lot more interesting than that. But anyway, on to our project. We were tasked with building an autonomous delivery robot, as I had previously mentioned, that can transport 2x2x2, so 8 cubic feet packages from our mailroom in the Student Union to Hoyt Hall. Our packages can be up to 50 pounds, and it has to sustain, weatherproofing, outdoor obstacles, anything like that. As you can see up here, we have our map. We have our primary and secondary routes, so that's kind of if you could visualize the campus from a bird's eye view from right there. I will also mention that this is a continuation from last year's project. A group of electrical engineers started the project and had the goal, same as ours, to build a delivery robot. And this is what they got done. They got the base done and some basic electrical components. So that allowed us to kind of hit the ground running, or I suppose rolling, right? So that was a real pleasure just to kind of have a head start on the project. So tonight we're going to take you through how we built the body, the eyes, and the brains of the robot. And to start us off, are some of our mechanical engineers to tell you how we got with the physical design.
Thank you, Nash. Hi everyone, my name is Zach Tresky, and I am here to talk about the robot's carriage, also known as the body. Now, the carriage was worked on by myself, DJ Mulroy, Andrew Nash, and Mackenzie Reber. So we met early on last semester, and we talked through the conceptual design stage. In this stage, we talked about 3 important questions: what, how, and who. What size packages should we deliver? How heavy can packages be? And also, who will mostly be interacting with our design? So we first talked through these parameters, and we decided that we want to deliver boxes that are in sizes of 2x2x2, 8 cubic feet in size. Also, those packages can weigh up to 50 pounds in weight. In addition, we knew a wide range of people would be interacting with the robot. Some professors that might have some underlying health conditions such as lower back pains. We want to make sure that the ergonomics are improved as much as possible. So we added things like a sliding drawer that we'll discuss in more detail later. So you're probably wondering, where do you even start where you're trying to build this massive carriage that can fit 8 cubic feet boxes and up to 50 pounds in weight? Well, it's kind of like building a house. And although I'm no expert on building houses, I have watched a fair share of HGTV shows, just as you all have, and took a few engineering classes that might have helped. Now, in these classes and in the shows, they always talk about one important thing. They stress that a good structure is built on a strong, solid foundation. So let's take a look at how that foundation was first built. So this is the carriage frame. Now, this is essentially the skeleton piece that makes up our robot here. And this carriage frame, it sits right on top of the robot chassis. That includes our drive system and our electrical components. And one of the first problems we thought about was how are we going to connect the 2 interfaces of the carriage frame to the robot chassis? And so we met with people in the machine shop, and we worked on the solution together that included taking angle iron pieces, cutting them down to size, and welding them into corners. So we have 4 corners that sit on the base and 4 on the top. And then we ran these long braces made out of slotted angle iron to start building our box where packages can sit inside. Now, DJ will take over from here. He's not here, but you'll still get to hear his lovely voice, and he will talk about how the walls, the door, and the roof were installed.
X100.
Sorry about that.
The carriage walls are made out of a light but durable thermoplastic called Kydex 100. An 8-inch sheet of Kydex allows for easy machining and fabricating using conventional methods and equipment, and has the desired strength and stiffness needed when fastened to the rigid metal frame. A large volume of material was used to create a carriage capable of holding an 8 cubic foot package. Kydex has a density 6 times lower than steel to help reduce excess weight of all material used. Overall, its high impact resistance to breakage and consistent color throughout the Kydex material helps hide scratches and wear, making it an excellent outdoor carriage material. The door was originally located on the top of the carriage, but the team redesigned it to be moved to the front. This feature, combined with an extending drawer, provides much better ergonomics for inserting and removing packages. The door is sealed with a foam rubber gasket and held closed by a magnet. The arch design of the roof is a relatively simple shape to manufacture, and its curved symmetrical shape has long been used as a structurally sound design that can support impressive loads. The interior of the arch is supported by 4 welded aluminum ribs to ensure durability in the event of an object or person falling on it. The ribs are bent at 90 degrees to meet parallel with the top of the carriage frame, allowing the roof to be mounted securely to the robot's frame. The design includes a curved arch that extends slightly past the robot's exterior walls. The purpose of the curved design is to direct rainwater off of the surface and to keep the interior of the robot protected.
Hi, my name is Mackenzie Weaver, and I'll be walking us through the interior features of the robot. So first is the drawer design. The drawer is composed of 3 different parts: the Kydex tray, angle iron support ribs, and steel drawer sliders. So the tray is made out of Kydex, bent and folded, and then supported with angle iron in the corners to help with structural support. And then underneath that lies the angle iron support ribs. These are an 1/8 inch thick and can help the tray carry the 50-pound package. And then beneath that, attached to the chassis, are the steel drawer sliders, which allow the drawer to move in and out. And then DJ will now explain the floor design.
There are a few important factors involved in creating the floor. It was important to seal off the electrical components to keep them protected. However, easy access to these internal components is needed for general maintenance and repairs. In order to meet these requirements, the floor is connected to angle iron framing that is bolted along the back axis, allowing it to freely rotate. The entire floor and drawer can lift up, much like the hood of a car, and be hooked to the roof in order to work on the undercarriage parts. When in use, the front of the floor is lowered back down and pinned in place, becoming completely fixed to support the drawer and the 50-pound pack.
Another important aspect of the design of the robot is how we were going to manage the heat. Some of our electronic components produce quite a bit, and so we needed to make sure that under a full load or maybe warm temperatures, because it does get pretty hot during the summers here, that the heat wouldn't be too dangerous for some of our components. Specifically, our batteries and motors. Our batteries having a maximum operating temperature of about 30 to 35 degrees Celsius, which is about 90 degrees Fahrenheit. So we looked to other methods, specifically PCs, personal computers, and how they manage to cool down their valuable and heat-producing units. And they use a combination of conduction with their heat sinks and convection with a series of fans. So we thought that we could do a very similar thing. So upon doing a thermal analysis, we determined that a combination of both convection and conduction would be sufficient. So we put 200 CFM fans blowing directly across the surface areas of both the batteries and the motors to keep them cold. We were also kind of concerned with where we were pulling that air from. We didn't want to pull directly from the outside, potentially rainy, snowy, moist air. So in order to keep the dry air, we created a partition towards the back of the robot that the fans can pull air down and create a nice circulation within the carriage of the robot. This, in conjunction with the conduction from the aluminum walls, creates sufficient heat dissipation that keeps the at-risk components safe. As you can see here, upon testing, the batteries are kept at a very pleasant 67 degrees Fahrenheit, and the motors at a much warmer but still acceptable 96 degrees Fahrenheit. Now we're going to take you through some of our exterior features and how we handled some of the problems that are located outside the robot. First of which is door interaction, how our robot is going to interact with 3 sets of doors between the mailroom and Whitehall. All those doors are unique, and so it created quite the challenge for us. And we wanted something that could handle, of course, those 3 doors, but also potentially other doors on campus to potentially extend this project to other buildings on campus. So we wanted something that's universally applicable. So our first thought was maybe a doorman, but that wasn't a very engineering solution, nor do we have money for that. Our next thought was a robotic arm that maybe we could put on the top, reach out, grab doors, and go through them. But upon further examination and more thought, that's quite a complicated process to be able to identify a door handle or lack thereof, or door knob, and so forth. And while I have no doubt that we could program a robot to do so, it would be quite complicated, and for some reason, administration didn't give us $90,000 in our budget to purchase a 6-axis industrial robot. So we went back to the drawing board, and we settled on a design that was a single-axis, rack and pinion-driven manipulator that is capable of locating handicapped door buttons and reaching out and pressing them, getting out of the way and going through. This made it so that we can use any door on campus with handicapped door buttons with a simple extension and then proceed. Next up, we're going to tell you how we gave our robot some eyes and some more about the sensors.
Thanks, Nash. So in addition to opening doors, like Nash said, we wanted the robot to be able to see things. So we gave it some eyes. And when I talk about eyes, I really mean sensors. So first up, we have the LiDAR sensor, then also the PIR sensor, and also the time of flight sensor. Now, I won't talk in great detail about how these sensors see things. We'll talk about that in more detail later. But from a mechanical standpoint, I'll tell you guys how I mounted these sensors and why I placed them in certain positions. So first up, the LiDAR mount. So the LiDAR mount needed to meet 3 important design parameters. First, placement. Second, angle, and also adjustability. So placement. We needed the LiDAR mount to be placed somewhere in the front of the robot as high as possible to get a good bird's eye view of its surroundings. Second, angle. We wanted the LiDAR mount to be able to tip forward and backwards on a single axis. So in the mount, what I did was I drilled holes along the sides of it, and I placed bolts through that. And from there, we were able to pivot it forward and backwards and then lock in place with nuts on each end. However, in order to improve upon that design, I wanted it to be more specific and have an adjustability aspect to it. And so I also incorporated a bolt hole pattern on the sides that ranges from 0 to 90 degrees in increments of 10 degrees. So now that when we are testing the angle position next year, we'll know the exact location and angle it's pivoted at. In addition to that sensor, we also have the PIR sensor. This sensor, it sits in the front of the robot and essentially detects people, and it will stop if somebody is too close by the robot. Now, this sensor needed to be placed somewhere high enough where it could see people. So together as a team, we thought about 3 feet from the ground is about the average torso level of a human, so it would be easily able to detect them. And last, we have the time of flight sensor, and that sensor is located on the back of the robot. The main function of this sensor is essentially to act as a sensor when the robot needs to back up into the charging station, which David will discuss in more detail later. This sensor is low enough to see that charging station and is also protected by being placed on the inside of between the back Kydex wall and inside the partition wall. And there's also a lens that sits in front of this sensor to protect it from rain and water. Now Mackenzie will talk about some of our efforts in weatherproofing the robot.
So the robot will spend a majority of its time outside traveling between Hoyt and the Student Union. So it needs to be sufficiently weatherproof so that water doesn't get in the robot to damage the packages. And we did 3 different methods for waterproofing the robot. First was we used a black silicone sealant to seal both the Kydex panels to the end to the frame. And this ensured that it was flexible enough for when the robot's vibrating that the sealant wouldn't crack or fall off. And then for the roof and all the sensors, those were sealed using a clear silicone sealant so that the sensors would still be able to detect the different frequencies and wavelengths applicable. And then lastly, we used rubber strips and an automotive weather seal strip in between the door and the frame, as well as the interface between the chassis and the carriage. And David will now talk about the charging station.
So a vital aspect in the world of robotics is power management. and specifically how the robot is to be charged. Without suitable method of power, this complex machine becomes nothing but a doghouse. So the mail delivery robot was built to be a fully autonomous mobile robot. And to be fully autonomous, we need an autonomous method of charging. This proved to be quite a unique challenge. Our solution is to have electricity pass from a charger through pins which contact plates mounted on the robot and then deliver that power to the batteries through a relay system. On the left, you can see that charger in line to contact those metal plates which are mounted on the robot on the right. When designing the charging station, we had certain design goals. We wanted it to be affordable, durable, and effective. And to be ideal, it should also accommodate real-world inaccuracies as well as be simple. When determining the method of charging, we found that in mobile robotics, there are two main methods of charging. That is wireless charging and direct contact charging. After further research into the price of both systems, we decided to go with the direct contact charging method and develop one ourselves, especially since the other one would have taken 2/3 of our budget. Our charging system is simple because it uses the same battery charger that was already being used, which you can see colored green on that top right photo. We convert it into an autonomous system by connecting pins to it. This allows us to use existing products with complex technologies that could regulate the amount of energy going out without developing our own kind. The pins we are using, which can be seen also on the top right photo on the front of that box, are spring-loaded what is called pogo probes. This means that we can be rotationally skewed up to 2 degrees and still maintain a solid contact. To account for potential horizontal and vertical displacement, those connection plates, which you can see on the bottom right photo, are much larger than required. We want our system to last for as long as the robot does, so we chose the connection plates on the robots to be made of brass, which are both weatherproof and can conduct electricity well. The charging station was also made so that the robot would run into the wall of the charging station before crushing the pins, because that would be bad. This was just in case the sensor were to fail. To ensure that minimal energy is lost through the series of materials between the batteries and the charger, copper is used for those pins as well as connections behind those metal plates. Now John will talk about the electronics.
Of the electrical components within the robot, one of the things we needed was a set of relays to facilitate the charging of the robot as we have, or to allow for use with the charging station. One relay disconnects the batteries from each other to allow for proper charging, as charging batteries in parallel is a bad thing. And the other two relays connect the batteries to the charging plates on the outside of the robot while we are close to the charger to allow us to charge them, but disconnect them when we are away so that we do not have battery voltage easily shortable on the outside of the robot. This is detected using a Hall effect sensor that is mounted between the charging plates on the inside of the robot's chassis, which allows us to detect a magnet mounted on the outside of the charging station. We also designed multiple circuits to supply the 5-volt power that was necessary to power the NVIDIA Jetson Nano computer that runs the more complicated localization algorithms and handles the large amount of LiDAR data that we need to process, as well as the smaller microcontroller, the STM32, that handles motor control. And here we have the circuit diagram for the power and signal circuit, which provides the voltage regulation for the computer components, as well as a lot of signal routing between them. And we have a fan circuit, which allows us to provide power to the cooling fans and allows us to turn them both on and off, as well as set them to high and low settings. And here we have the circuits mounted within the chassis, including the Hall effect PCB in its place between the charging plates. And now Anna will introduce us to the software side of things.
As you can imagine, sorry, I'm a little raspy. If you can't hear me, I'm really sorry, but I'm gonna try my best. So as you can imagine, on an autonomous robot, there is a lot of software. And one of the boards that we use to deal with this is called the STM32. If you've taken any EE classes, you've probably run into this thing. It's pretty common, and it's a lot of the other senior projects as well. And one of the things that we needed in the board was that it had a lot of pins that had certain capabilities. One of these capabilities is something called an interrupt. And this is important for our encoders, which go on our gearboxes so we can be really sure how far we travel. Another thing that we needed to make sure that we had was called pulse width modulation, and that's how we control our motors. When we went to run the motors for the first time, we realized that they were pretty bad. It kind of ran into a wall a couple of times, and that's when we figured out that we needed something to fix that. As I mentioned, the encoders are pretty good at that. So we wrote a motor control script using proportional integral derivative loops. These loops give us very accurate information about how far the gear shaft turns and how much we're moving. This graph is us comparing our left and right turning when we upgraded our PID values to make sure they were pretty similar. The main things that this did is it increased our time when we increased our RPM, so those lines are very sharp, and then it decreased those staggery things that you can see after the change. The only inconsistency that we had was at max RPM, where you can see the right is a little bit faster than the left, and we compensated for this in code by making sure our left motor and right motor's top speed were the same, by lowering our right motor's speed. The STM is completely abstracted from all of its code. It doesn't do any special thinking or anything on its own. It gets it all from the Jetson Nano via USB input and out, which Marissa Metallo is going to introduce to us.
Thanks, Anna. As mentioned, I'm going to talk about the Jetson Nano, which is the brain of our robot. It's a computer that does all the processing. We have several sensors that are connected to our Jetson Nano, and those sensors feed the Jetson data, and the Jetson does processing to decide what to tell the motors to do. One of the first sensors is LiDAR, which is light detection and ranging, which surveys the environment and sends ranges of distances back to the Jetson Nano so that the Jetson Nano can do a proximity check to see if there's anything within 1 foot of our robot. Additionally, we have a passive infrared sensor known as a PIR sensor, which says infrared object detection, which we use to detect any people walking in front of the robot. The PIR sensor can see up to 3 meters, but we're able to adjust that distance with a potentiometer. The time of flight sensor is another laser sensor that is used to send distances back to the Jetson. So when our robot is backing up into the charging station, we can cut the motors whenever we are 280 millimeters close to the charging station. Then we have our GPS RTK, which is how we get the robot's position at all times. So it reports the longitude, latitude, and accuracy. The accuracy is typically within 2 centimeters, depending on how close we are to the base of the GPS, which is mounted on point, which is where our robot usually begins starting to go pick up a package. All of these sensors send its data to the Jetson Nano, and those control the motors, but it has to do that through communication, which it does over a robot operating system, which Matt will talk about.
So as Marissa mentioned, the Jetson Nano is the central brain of the robot, and ROS is the software ecosystem that we use to manage the system as a whole. In ROS, there are 2 important concepts. Nodes are simple processes that run on the Jetson that do some kind of computing. And for us, this manifested mostly as simple Python scripts that are each designed to manage some part of our robot. Topics allow nodes to communicate between each other by sending forms of data onto a name that is associated with it, and then any other number of nodes can receive that data and use it in their own processing. In our system, when we went to design it, there were 2 big nodes that we started with: the autonomous navigation and the manual driving. Autonomous navigation is when we navigate between our GPS waypoints to go from Hoyt Hall to the SAC. This is the main use case of the robot. But we also needed to be able to manually drive it in case it gets stuck in the grass or just for our own testing. In addition to these nodes, we made nodes for all of our other inputs as well. This includes the LiDAR, the GPS data, all of our sensors, and a UI that we use to control the robot manually. All of these publish their data over the topics, and then they are received by the respective control nodes, which then publish our motor control to the STM32. Up next, we'll show you a few videos of the robot in action.
So right here is the door interacting with one of the handicap door buttons in our student union, just a brief little clip. And then backing into the charging station, which this is what we talked about, where it uses its time of flight sensor to detect how far away it is. Has to go real slow because it has to be extremely careful. The pogo prongs are quite small. Yep. And with that concludes our presentation. Are there any questions that we can answer for you?